Sarah Aerni is the principal data scientist at Pivotal. Sarah, welcome to Software Engineering Daily.
Hi, thanks.
I want to talk about your work at Pivotal, but first I'd like to ask a naive question. What is data science?
I guess it's not really a naive question. It's a question I think that's appropriately asked because it means many things to many people. At Pivotal, we focus on data science really being kind of machine learning and statistics applied to very large data sets, encompassing actually the underlying understanding of how to process in a parallel fashion on these enabling technologies that exist, like distributed databases or Hadoop, things like Spark.
How does the term machine learning relate to data science?
You can think of it as part of the repertoire of algorithms, essentially, that you're going to use. So ways for you to interpret or understand what is going on in the data by building a predictive model. And machine learning kind of has a lot of different algorithms and a lot of people working in that space developing new approaches that allow you to either combine features or attributes that you can extract out of the data about individuals, for example, and their behavior to predict something or to separate them into subpopulations.
I read an article by a guy named Robert Chang, who is a data scientist at Twitter, and he wrote a Medium post where there was this two types of data scientists. He called them analysts and builders. And he said that the analysts make sense of the data, and they operate more like statisticians. And the builders construct software systems and models and recommendation engines. Does this sound like an accurate framing to you?
Again, I think everyone has a different interpretation of what it means. I feel like it's hard to divorce those two pieces from each other. I think anyone who operates in the space does a little bit of statistics. It's probably hard to not understand kind of whether or not you believe something is sound or I guess test whether or not some hypotheses that exist within data are true. So I feel like you can't remove data science from statistics, even if you are on kind of more of the implementation side. I guess to me, maybe that's separating somebody who's a data scientist from maybe like I guess what I consider machine learning engineers. So if you're somebody who's maybe figuring out how to implement an algorithm at scale and not concerning yourself as much with building a model, learning about the data, extracting features or insights from it, and then sort of feeding that back into a loop. But really more around how do I implement this particular method, then I guess it's just kind of crossing over into a pure engineering space. And I think there's a spectrum.
So I would love to begin to creep towards a discussion of those engineering practices. What is Pivotal?
Sure. Pivotal is a software company. We do have a lot of engineers. Those are engineers that either dedicate their time, and they can, of course, split their time within Pivotal Labs itself. We have, of course, this practice that is both outward-facing, so we consult with companies that are trying to develop maybe a new application, or they need to learn how to do application development a bit differently. So they can work with customers, or of course they can work internally on our own software that we produce, like Cloud Foundry, which is sort of platform as a service, as well as our data products, including our Greenplum database, which is a distributed version of Postgres, and then Hawk, which is that database sitting on top of HDFS. So we sort of have engineers across the board there. We also have a machine learning library, MadLib, that allows you to, for example, build regressions on billions of rows of tables. So I think that's kind of more the traditional engineering portion of what it is that we have at Pivotal, and these open source software tools that we develop as well.
So you mentioned two data storage products. One was the Greenplum database, and another one was a product that's built on HDFS. Can you describe these two products in more detail?
Sure. I think probably best to check out pivotal.io for all of our data stack. But as far as kind of the history of Pivotal itself, we are composed out of assets from EMC and VMware. VMware really is where Cloud Foundry, for example, came from. EMC is where we had Greenplum, which is a distributed version of Postgres, so basically forked off of Postgres some 10 plus years ago, when it became clear that running these large analytics queries on a single node isn't going to function as our data grow to terabytes and petabytes. And so as we're approaching those larger numbers, of course, it makes sense to figure out how to split up any sort of query that we run. For example, if you wanted to look at a large table, let's say it's all of the names of all of the people ever on Earth, and you're curious to know maybe the distribution of those names. Going through a table on a single node of billions of names is going to be quite painful. And so if you distribute that data and allow it to live on multiple nodes, you can ask those queries to be operated on by all of the individual nodes on their own local data. So each node independently can count the number of times it has any particular name appear, and then that can be aggregated up as sort of a sum of sums. And that's really where Greenplum is originating from. Over time, of course, with the evolution of advanced analytics on top of that, we worked together with Joe Hellerstein at Berkeley to create MadLib, which is an open source machine learning library. And that is really the foundation of kind of the machine learning side of the house that we have, where ultimately it allows us to build models off of extremely large tables that now, rather than only containing kind of information that you might be wanting to run, I guess what we would consider traditional kind of BI queries on, which are of course very important to be able to understand what's happening in your data, but actually build a predictive model. For example, predicting how long a patient would be in the hospital using a lot of historical data.
And how much do your enterprise customers need to know about computer science and machine learning in order to leverage these products?
Not necessarily too much. So it depends on the expertise level or kind of the set of tools that they have that they work with. So we have people that really just point Tableau at it and use it that way. So that's, I think, someone who doesn't need to really understand much except, here's a table and I want to visualize something in it. Then, of course, we have the other side, people who are engineering new products and are potentially trying to figure out how to build a new algorithm. So it would be the other extreme where you probably have a very good understanding. And then there are people in the middle, especially in the data science space, who want to use things like MATLAB, who want to write SQL queries. And although you don't necessarily need to know everything about the underlying architecture, because really you're just writing Postgres queries and allowing the query optimizer to figure out what's the best thing to do given the way your data is shaped. It is, of course, always beneficial to be a bit faster. And certainly in the instances that we run into at times where an algorithm may not be already available in MATLAB, and maybe you want to use Python or R and all of its libraries, we have the ability to use procedural languages, since again, Greenplum is Postgres, to run R and Python in this parallel architecture, meaning a lot of smaller R and Python jobs. We've done it, for example, running millions of smaller models in parallel across the many nodes. And at that point, I think you do probably need to have somewhat of an understanding of distributed systems, although again, not to the extent of, I think, the way it used to be in the high-performance compute world, where you maybe needed to know how to multi-thread a process, lock threads, and sort of communicate information across. That's sort of all still removed, and you can operate seamlessly on the data.
What's the onboarding process like for an enterprise customer that wants to start using Greenplum or another Pivotal product?
We have a variety of ways of onboarding people. And again, I think probably best discussed by our product team. On the data science side, we do a lot of training for the data scientists to enable them by offering training directly on their data if they'd like. So we can build models with them. We can help run kind of a hackathon on data or data jam where we essentially teach them how to use our tools, teach them how to use other tools on top of it, and then have them go off and try and do something really cool in a week or a few days to just sort of experience it.
So you mentioned some machine learning libraries built within Pivotal, and the adoption of distributed data platforms like Spark have enabled these types of machine learning libraries. Can you describe how these machine learning libraries take advantage of a tool like Spark?
So I get it, if we're just going to generalize to how these distributed compute paradigms work and not necessarily worry too much about whether it's sort of an in-memory system or a kind of more traditional MapReduce where it's writing to disk. But the concept of being able to distribute data across nodes and operate on top of it, some of them allowing you to be quite in control about how data gets moved around, and others where it's a little bit more seamless. At its core, what you're trying to figure out with the libraries and all of these implementations is how to break a problem up into a lot of what we'll call embarrassingly parallel jobs. So essentially, what you have, let's imagine you have a billion rows, and you're interested in running a linear regression on top of that. There are certain pieces of the linear regression where you're doing computations on each row that can be operated on in parallel across all of your nodes, meaning, for example, the product of a feature vector against itself, which is one step. So that can be run actually on all of the nodes in parallel, whether that be kind of splitting it up using Spark or MapReduce, whatever it is that you're wanting to do, or, in our case, using the database itself and the way it stores the data. So we, of course, have pieces where ultimately the underlying chunks are running SQL queries or maybe small Python code on top of each. And then they sort of shift the data around at a minimal level to then come up with a final solution. And of course, any sort of instance where you think about running a lot of smaller jobs, maybe it's sampling on smaller subsets, those things can be done in parallel across the nodes. K-means clustering is another easy example where sort of you're trying to compute the distance to a centroid for every example. Every example doesn't need to know about another example to compute that distance. So through each loop, and at the end, you aggregate that information by sort of moving those centroids around to the, kind of that midpoint. So iterative, but distributed.
Can you talk in more detail about the difference in use case between when you would use Spark and when you would use a more batch processing framework like Hadoop MapReduce?
So, I would argue that Spark is still batch. In a lot of instances, it's just kind of the way things run. If you're wanting to do something that's a bit more like transactional and fast, then you might be going to some other sort of like in-memory data grid. I think the usefulness of Spark is anytime you're doing something that requires iterations. For example, that K-means clustering, and you want to keep things in memory as much as possible. Whereas MapReduce, really, you write to disk all the time, and it becomes kind of an I/O issue. So think about something that kind of streams through an entire process where you're writing to disk. That could be much slower, but it's also sometimes there have to be considerations and probably worthy of testing. Until there's kind of a full understanding about what is faster or another, to try and test out and see what is actually faster. Because of course, in any paradigm, you are still relying on kind of the underlying the way things have been engineered to shift and move around the data, which can become a network issue as well. There's sort of that shuffle period that you have to kind of trust, and so decide, what is most appropriate.
I think you just defined something that's really useful, which is the idea that in Spark versus MapReduce, Spark keeps things in memory after you've done a certain phase of whatever pipeline of processes you're doing, whereas Hadoop or MapReduce just finishes the job that it's doing and then writes it to disk. So with Spark, you can create these elaborate multi-stage processes, which can be really conducive to machine learning, if I understand correctly.
Again, I don't want to generalize too much. I think it's probably best to firstly, I guess the best source would be Databricks, as they are, the company that sort of outwardly promotes and develops and works on Spark, and can educate very broadly on what to do. But at the same time, I think the use case, it's a case-by-case basis. I think what we acknowledge at Pivotal is that there is kind of not at the moment a one tool fits all, and it's always important to consider what your use case at hand is. If there's something that simply doesn't exist currently in MLlib, maybe you want to run a lot of different smaller R jobs. Maybe you're wanting to, actually just process a bunch of images in parallel and batch and extract features out of them. That's actually quite appropriate for a MapReduce job. If really what you're doing is taking terabytes of images, just a lot of small ones, and recognizing faces on them and then just keeping them there for future use. That's something where you could write a MapReduce job and leave it. You could, of course, do it in Spark as well, but if it's just sort of one step, there might be limited utility to forcing it into Spark when Spark is better used at that moment for something else. So I don't want to generalize. I think there are probably places for a lot of the different types of paradigms out there.
You wrote a post recently called Using Data Science to Save and Improve Lives. I think you co-wrote it with a few other authors. What is the lowest hanging fruit? What are the problems which data science can definitely help us solve in the near future?
In healthcare or across the board?
Across the board. Whatever is the most lowest hanging fruit that comes to mind.
The lowest, data science has solved a lot already, I guess. So I feel, the thing that I think most people jump to all the time is recommendation engines. We can recommend almost anything based on behavior. And it's, I think at this point, almost commoditized. It's like easy, there are tools out there. And,
okay, sure. Let's talk about health. Health seems more interesting. I guess the lowest hanging fruit is almost most obviously the not interesting side of things.
Probably already there.
What advertisements do you want to see?
For data science. So healthcare and life science near and dear to my heart since I have a background in that, and I think you also do.
Yes.
So I think for me, right now, the focus area, certainly in the United States, within the healthcare system, I think is around kind of legislatively driven opportunities to improve healthcare outcomes, to lower costs. And it's funny because I think when we think about, of course, from the nice perspective of trying to improve healthcare outcomes, we've done work predicting whether or not somebody will crash. So there'll be severe physical deterioration of a patient. So you'd want to transfer them into the ICU if they're in a hospital, so that they'll be taken care of in a better way. So that's one of these that's quite critical, but isn't necessarily a low-hanging fruit in the sense that, on the other hand, you might be wanting to predict whether or not a patient will be readmitted to the hospital, which of course is also a very important piece. But it's something where really, hospitals are getting dinged for this. So they need to know if they're going to discharge a patient from the hospital, is this patient likely to come back within a certain period of time, and therefore I will have to pay for those costs because I let them go too soon. It's probably one of the most, maybe not lowest hanging fruit necessarily, because you could still go back to recommendation engines with even healthcare, but it is certainly one of the ones that's being driven very, very forcefully by kind of the requirements and reimbursement.
Is it harder than it should be to gather, do aggressive data science on health data because of the state of confidentiality, like HIPAA requirements, and the difficulty of truthfully anonymizing health data?
I think in terms of doing collaborative data science, yes. But within any particular hospital, they of course have access to a lot of the data and are able to keep it sufficiently secure. I would argue that as secure as healthcare data is, I believe probably financial services data is even more secure.
So if all health data was magically released tomorrow, and was anonymized to a successful degree, what would we be able to do with that data? Do you think there would be a fleet of data scientists that would be able to hack on it and do some amazing things?
That's an interesting question. Assuming that we can solve for that entity resolution problem of actually recognizing patient A in 2 hospitals, which is kind of in and of itself a big data science problem. I would argue that there is such sparse information captured on a lot of individual patients that it's actually not totally inappropriate to try and focus in a bit, on episodes of care. So being able to say what will happen to this patient right now as they are in the hospital. I would argue that in today's state, there's so little that we actually know, for example, about the role of genetic variation in disease, for example, and in outcomes. We have very specific examples where, even a genetic variant within cancer can determine whether or not you can take a certain drug. But kind of on a global scale, it's at some point it's even a sample problem. Like if we had data on everybody in, at the genetic level in the world, would that be sufficient for us to answer all of the questions? No, I'm sure not.
So one quote from your article says, quote, "Patient records are also growing with advances in genomics." What information about patients are we learning from new genomic science?
Well, of course, we can consider that kind of familial history in the sense that we have access to what it is that they have inherited in terms of some conditions. So we do know that there are, for example, variants that make it extremely likely for patients to develop breast or ovarian cancer over a lifetime. And that, of course, is critical because you might undergo prophylactic treatments to avoid developing that, or to lower your chance, at least, of developing that. So as that information, as that data grows, of course, that's one example where there are very specific subcategories, but it's even what happens to you over your lifetime. There's a very famous article where a researcher, Mike Snyder, sort of published everything, not just his base genome, meaning his variants, but actually seeing changes over time of what we call gene expression, but we can think about how much of that genome is active over time that allowed him to trace, and in addition to some other measurements, for example, watch himself develop or become pre-diabetic. And then acknowledging that, there also was a variant or predisposition for him for a particular medication that he may or may not react well to. So, as that information grows, as we have more patients with that type of data, we can try and make different decisions, but hopefully also try and understand, as we look at lab values, for example, are your low platelets as a result of a genetic variant or because of some sort of environmental condition. So I think it's really not just the collection of, your family history, but also these things that happen to you over time, tracing changes. Is your blood pressure changing a lot, or is this just your baseline? Trying to collect that data is also critical.
Another quote from your article is, "Both consumer wearable and in-hospital sensor data is growing in granularity, increasing in scope, and becoming more pervasive." End quote. And I'm curious if the volume of data being collected here outstrips our ability to write algorithms to actually analyze that data.
Oh, that's a great question. And I also definitely want to credit my co-authors here, Gautam and Julia, who contributed to this article. And I believe one of them probably actually contributed that particular quote. I think what we're seeing, and this is something that's happened for a long time, when you think about the foundation and the history of almost everything that we do in the field of statistics and machine learning, as it evolved, originally we were dealing with very small data sets and trying to derive value and understanding out of very small data sets. And you are absolutely correct in saying that as those data volumes grow, everything that we know and understand is going to change because we're going to have access to a lot of different data sets. So while, traditionally, historically, we might have said, hey, there's only one model that's going to kind of fit all. If we assume, we're going to predict housing prices, well, it might be that we can include interaction terms about this zip code. For example, San Francisco's housing market is extremely different from, I don't know, say, Little Rock, Arkansas, I would assume. But that we need to start gathering subpopulations, and what we see that over time are the algorithms we generate, yes, have to try and address the problem of data scale, but potentially over time we're having to understand anomalies within the data as well that, maybe we would have tossed those out, but over time as data volumes grow, maybe anomalies are actually more meaningful subpopulations that may evolve that we might want to consider.
Interesting. So medical imaging is also changing due to data science. And one way I think about this is radiology is a field where a computer is often better than a human's naked eye at identifying problems, but a human working together with a computer performs even better than just a computer. So I'm curious, we're currently in the state where human-computer interaction is fantastic, but are we going to see a day where a computer is simply better than even the human working with the computer? Like the computer alone will just do a better job?
It's I think that is like a fear that a lot of people
I know.
are kind of putting out there, that we should fear AI.
Fear mongering sells podcasts.
Yeah. I don't know. I don't want to claim any way. I think maybe you're referencing things like deep learning that have kind of allowed us to take away what we consider, I think, the fundamental human element that existed in machine learning, which was this concept of feature engineering, or extracting those variables that you're going to put into an algorithm. When you think about something like housing prices, again, let's go back to that. We're doing a linear regression trying to predict how much a house is going to cost. Of course, you'll sit there and think, okay, well, I care about, the number of square feet, the bedrooms, the bathrooms, maybe other things that you can measure about the neighborhood. And those were things where there was this portion of human intellect that went into it. So not just the human-computer interaction that you're speaking to, but actually the part about designing what is going into it. And, in the space of deep learning, we're essentially saying, no, let's not even ask humans to try and understand the patterns that might feed into something. Let's allow the machine to actually get down to the pixels and determine what is there. Beyond that, trying to sort of have humans feedback, I guess the only thing I would hope is that the desire that kind of AI is built to serve people and not machines, although that's not true with Internet of Things, but still, I think hopefully the fear part is removed, but certainly it could improve.
So you took a very objective phrasing there with the saying, we're removing the human intellect. I would say, and maybe you would disagree, but I would say that the human intellect thing, you're kind of using that as a euphemism for human error. Don't you think we understand psychology well enough to sort of hand off that aspect to the computer and say, deep learning, you can do this?
So do you really think it's human error there, or is it a human's capacity of cognitive limitation to be able to actually see certain things?
I think that we overestimate our heuristic abilities, and I think I'm pretty sure that our computers can if they can't settle on the same types of heuristics that we can right now, eventually they'll be able to in the near future.
That's interesting. I look forward to it.
Man, you are totally diplomatic. Very diplomatic. So I saw the slide share that you presented called Internet of Things, How Data Science-Driven Software is Eating the Connected World. And on one slide, you had a picture of an oil rig disaster. How can Internet of Things work together with data science to prevent disasters?
Yeah, so that's, absolutely, that is just one of the examples. And I think the earlier one that I gave with kind of an individual's disaster of deteriorating, so crashing at the hospital, and trying to prevent that. What we have is the ability to allow sensors to alert us about what's happening around us. And I think historically we would say, something's changing with the heart rate. Let's wait until it reaches a certain threshold and alert. The pressure builds up too much. Let's alert. There might be a disaster coming. But really, if we have a lot of different sensors available to us, rather than waiting until it's reached what we consider, I guess going back to your earlier statement about a machine versus a person being able to understand and create these rules, we've reached a danger point. Statistically, at this point, it's going to explode soon. Instead, allowing all of the sensors that are there predict an event that has happened in the past and trying to understand how all of these sensors together actually give information. That can then lead to an outcome. And, in that talk, we actually talk a lot, not just about the concept of building a predictive model, so saying, there was a failure and how can many of these sensors come together to predict it, but actually going sort of into the nitty-gritty still about how there does have to be this component of human engineering of features. How do you take some sort of a time series data and turn it into something meaningful to predict an outcome? So still that need. And actually, I look forward to Gautam will have a lot to say on this space, as he's doing a lot of work in that sensor space right now, predicting failures and maintenance issues. So it is definitely an exciting space.
Do we have the server capacity to store the Internet of Things data? Like, I'm curious if our server capacity is growing at a rate that is commensurate with the sensor data growth.
I'm sure EMC could speak more to that. I mean, they're in the storage space and they can speak to it. I myself have not paid too much attention to it. I kind of am a user of this and sort of allow other people to architect. I'm sure that, if we look at how much data has been generated in the past year as compared to all of history similar to kind of human growth, we're looking at something pretty immense. And of course, there are a lot of really exciting things that have sort of been evolving over a long period of time. For example, even DNA computing, trying to kind of store data in a different way. So it's not just bits, not just binary, but kind of other ways to store data. I also look forward to seeing what happens in that space. But it is, of course, alarming rate of data growth, absolutely.
Yeah, and yet the costs have continued to go down.
Mm-hmm.
So I guess that's promising. How hard is it to take a high volume of sensor data and build a predictive model?
So easy. It varies. I think, again, going back to that statement around, how it is that you transform kind of time series data or anything into a feature that will go into a predictive model. What's interesting is there are a lot of tools out there that try and solve for this problem, to try and kind of remove that human element to need to understand what it is that we're looking at and extract these features. And there are plenty of companies to kind of explore in this space that try and look for interesting other dimensions to explore. Sort of less something that I focus on.
This week of shows on Software Engineering Daily is about women in tech. And I'm curious, do you think this is a topic that needs to even be discussed explicitly, or is it more of a topic where the way to impact the situation of women in tech is to simply showcase women in tech talking about their technical achievements rather than talking about any controversy or female marginalization?
I think that's an interesting perspective, and I did participate in a few kind of conversations in this space, and also even contributed to an interview where other women were interviewed in this space. I think, as with anything else, it is important to focus, of course, on all of the contributions of any individual, regardless of who it is, and sort of whether that is gender or race, it's sort of irrelevant. I think calling, an individual out just due to some sort of an attribute, of course, is, it's interesting. I think when we focus on, a woman did this and what that means for women, it is very empowering for other women, I believe, who want to be in that space, who then have peers to look toward. But at the same time, it also, of course, I think inherently women tend to also become a little fearful that, they'll be called, that they were called out because they were women. So I'm not sure if there's sort of a good solution to this space. I don't ever think that there's anything negative to calling out, how a group may feel or be perceived, to bring awareness, just the same way that we try to bring mindfulness to other elements of our lives. For example, Apple brings mindfulness to how much we move by putting kind of a step tracker in our phone. So I think just for everyone to become conscious, and I think in many ways anyone could be guilty of this, to remind ourselves that, everyone is deserving of praise for the work that they do, irrespective of who they are, and to be respectful of people's differences. And sort of just relying solely on sort of one basis for differentiating individuals can be dangerous.
So speaking more explicitly, are women on an uneven playing field when they enter the software engineering field?
I can't speak to software engineering as I am not necessarily a software engineer. On the data science side, I think, and this is something that I've called out a lot, I think there are a lot of very visible women in data science, Monica Rogati being one of the easiest ones to pull to sort of point out. who was there early on with a set of male peers at LinkedIn. So I think it is a space that feels very open still, and I think it's important to maintain that. But I wouldn't say we have an uneven playing field, because I think I said this once before, data science is specifically about, in a lot of ways, being interdisciplinary, thinking outside of the box, taking someone's business expertise and some technological understanding and bringing that kind of to a center. And so in a lot of ways, diversity in thinking is so critical, because coming up with new ways and new approaches and having those conversations where it's not just single-minded focus actually means that it is a very interesting space in which to have a lot of diverse backgrounds, in any regard, also in what you've been trained in. Are you someone in operations research? Are you someone in biomedical informatics? Bringing those groups together actually allows for a lot more ideas to flourish and a lot more approaches to be developed.
I mean, I completely agree with that, but I have a hard time thinking of a field where diversity of opinions is not a good thing. And yet I've seen plenty of, ostracism or marginalization or whatever you want to talk about of women in software engineering, and I know diversity of opinion is super important there too, because if you end up with a crappy solution that's just hive mindy, it's bad. So that was kind of my motivation for doing this week, is like I've just seen so many times where I'm like, this ostracism or this negativity towards women, even if it's subtle, is counterproductive. But
it is. Any ostracism is counterproductive, but I think what I'm saying is data science is a field born out of, diverse thinking, out of
and recognizing biases.
That's interesting, yeah. Although, in that sense, some other fields are the same. I think it's really that field itself already is bringing together people with such diverse thinking. And so it's interesting in that sense. I always feel everything is welcomed. And it's not to say that people, and there are women that don't feel potentially marginalized. I can only speak for myself. And of course, I think, any respect, I think anytime something occurs, it's easy to fall back into the mindset of, this is because I am. But it's also really important that when you have that moment to also step forward and realize, this is me and I need not hide it. I need to embrace it and allow it. Because of course, by denying that, for example, you're a woman and trying to sort of fit in and fit the mold, you're never going to quite succeed at being something that you are not. So instead, acknowledge it, try your best to celebrate it, and focus again on the task at hand.
So I'd like to close off by talking a little bit about academia. You spent a lot of time in academia, and I'm curious how the intellectual experience within academia compares to your professional career at Pivotal.
So what's interesting is my team is extremely academic in the sense that we all come from strong academic backgrounds as well. Not, a variety of PhDs and masters and bachelor's degrees across, different fields of studies. And we all bring that together. At Pivotal, we still have a lot of the same things that during my graduate school training were present. So we do knowledge sharing, we essentially lab meetings. On what it is that we've worked on. We ask outsiders to come speak. We still go to conferences. We read papers. We publish papers. So in that sense, Pivotal itself, specifically the data science team, still feels extremely academic, with that added benefit of having access to tons of data and a lot of really, really great technology.
Do you think there should be a closer relationship between academia and industry?
We have extremely close relationships with academia. As I mentioned, the MadLib library was developed specifically with Joe Hellerstein at Berkeley, and we have other examples. Chris Ray works on top of Greenplum database for Deep Dive, for example. And we do work a lot, actually. I had a collaboration with a researcher at Harvard Medical School to sort of assist in some of their research, and we have some other ones that are ongoing. I think it's an interesting balance because, of course, at the end of the day, industry has to concern itself a lot with whether or not they're profitable. But at the same time, it's so fascinating to me that when we allow researchers to access our environments, and we did have a large 1,000-node Hadoop cluster, the analytics workbench, that was open for research, and we did have a lot of research organizations working on top of it. So once you allow kind of young developing minds or researchers in a space to think about new paradigms and not have to focus on, I have to get this grant in order to get the software, it's so interesting because I think a lot of fields are kind of stuck to thinking in another paradigm, because of course that's what they have access to. And so they engineer or they build algorithms or they come up with ways to process their data in the paradigm that they have access to. And if you open their minds with new paradigms, access to new technology, that all shifts.
What do you think about this idea that it's like more noble to work in academia because you can be doing, quote, basic science?
Oh, I did a lot of basic science. I I think the concept of it being more noble is probably up to the person who's passionate about that topic. So I would say that there's a lot of very interesting work that happens at a basic science level that I think absolutely needs to continue occurring. Within academia. There is a lot of basic science that occurs within industry, for example, the pharmaceutical industry, but I think those two spaces interact a lot. The things that happen, I think, that are driven by companies that are concerning themselves with being profitable. Again, going back to the example of, the iPhone or Fitbit or anything that's out there that's trying to track steps. Yes, at its core, it's concerning itself with how do we become profitable, but the things that come out of it, research and understanding of movement, potentially looking at multiple sclerosis patients and seeing the way they progress. I think what's so fascinating is the way in that space, even though it's driven, of course, by, being profitable, at the same time, there are a lot of really, really interesting contributions that come out of it too.
Interesting. Sarah Aerni, thanks so much for coming on Software Engineering Daily. It's been fantastic talking to you.
Yeah, thanks so much for having me.